Hello, everybody. Greetings again from Vidyavardhaka College of Engineering. It is a pleasure for me to give the third and the last lecture with regard to foundation engineering, part of geotechnical engineering. The first two lectures, the emphasis had been solving the numerical problems of gate 2022. Some of them were solved, and now I'm going to continue further. I hope I'll be able to solve all the numerical problems related to foundation engineering by the end of this lecture. Therefore, what is that we are going to cover in this lecture? As I mentioned, the focus is on solving numerical problems of gate 2022. So we solved a number of problems which appear in gate 2022 related to bearing capacity, settlement, and shallow foundations. We also solved a few problems related to deep foundations, but there are a few more left with respect to that. And the deep foundation we normally deal with is pile foundation. So some more problems related to pile foundation, then stress distribution in soil, soil exploration, earth pressure. These are the areas in which I plan to cover the next portions of my lecture. Well, pile is a deep foundation. Pile foundation is used, number one, when the soil near the surface is not so strong, less strength, less stiffness. Two, the structure is heavily loaded. So you're going to transfer the loads from the structure to a soil which is below at a sufficiently deeper elevations through pile foundation. You should always know that piles are never used singly. They are always used in group. So let us say that a single pile has some capacity, say Q, and there are n number of piles. Say the capacity of a single pile is 1000 kilonewtons, and then there are 10 piles. What is the group capacity? Will it be 10 into 1000, 10,000 kilonewtons? No, not at all. It will always be less than 10,000 kilonewtons, less than n into q. And hence, how much less is mentioned in terms of pile group efficiency. And you have a simple formula. Qg happens to be the capacity of the group of piles. N is the number of piles. Q happens to be the capacity of single pile. And eta G is the pile group efficiency. As I said, you're going to always use piles in group. There may be two piles also, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and more can have some order like this. The objective here is that as far as possible, the spacing is reasonably well maintained, and they are going to be spread in some pattern. The piles are going to be spread in some pattern. And whatever you see here is the plan view of piles kept in group. Now you need to find the efficiency. Why? Because you want to know the capacity of the pile group. And that is what is required from the design point of view. So you follow different types of empirical rules for that. Pile group always has the efficiency controlled by the floating portion of the pile, by the pile which is in contact with the neighboring soil. At the base, you don't have the problem. Normally efficiency will be 100%. That means base capacity of single pile, if it is Cx, total capacity of n piles at the base will be n times x. The problem is always with respect to the portion which is on the surface. And usually, the geometry in which the piles are kept, the diameter of the pile, the spacing of the piles play an important role in stating or providing the capacity. And here is one of the empirical formulae given by Converse and Lebarre on pile group efficiency. And group efficiency eta G is equal to 1 minus theta into n minus 1 into m plus m minus 1 into n divided by 90 times m into n. So total pile group's capacity is equal to eta G into sum of the capacities of individual piles. Here you should know that m is equal to number of piles in a row, n is equal to number of rows. Theta is given by tan inverse of d by s, where d is the diameter of the pile and s is the spacing between the piles. So n, m, s and d are required to determine the group efficiency eta G. Therefore, eta G group efficiency is equal to pile group's capacity Q times du divided by summation of Qu, which is the sum of the individual piles capacity. So eta G will always be less than or at the most equal to 1 or 100%. As I said earlier, there is no effect on the end bearing, but for the frictional component, geometry, how close the pile in question is to the neighboring pile, the diameter of the pile, etc., they play an important role in deciding the group efficiency. So there are a number of empirical formulae like the one which I mentioned, Converse Lebarre, but I always love this particular empirical rule, Feld's rule, which simply says that efficiency of the pile is reduced by the neighboring piles. Each neighboring pile is going to reduce the efficiency by 1 by 16 times. So if there are 3 piles close to it, then 3 by 16 is the reduction in the efficiency. So 13 by 16 is the group pile efficiency. So Feld's rule is very comfortable. You don't require to memorize the formulae. And according to Feld's rule, if let us say there are 3 piles as you see here, each of these piles is influenced by 2 neighboring piles. Therefore, eta G is equal to, there are 3 piles, each of these is influenced by 2 neighboring piles, therefore 1 by 16 from one, 1 by 16 from the other, totally 2 by 16 is removed, therefore capacity is 14 by 16 divided by total number of piles, that is 3. Therefore, efficiency is 87.5%. Let me take this case 4. Here there are 4 piles. Each one is influenced by 3 neighboring piles. Therefore, efficiency is reduced by 3 by 16, or the efficiency is 13 by 16. 4 piles into 13 by 16 for each of the 4 piles. But now, you take the next one. There are 6 piles arranged like this, 3 in a row and 2 rows. The corner piles are influenced by 3 piles, are affected by these 3 piles. Their efficiency is reduced by 3 by 16. But these 2 intermediate ones are influenced by 5 piles. Their efficiency is reduced by 5 by 16. Therefore, 4 into 13 by 16 plus 2 into 11 by 16 divided by total number of piles given in percentage, it will be 77%. Let me go to this one. So there are 4 corner piles. Each is influenced by 3 piles. Therefore, efficiency is 13 by 16. There are 4 intermediate piles, each of which is influenced by 1, 2, 3, 4, 5. So efficiency will be 11 by 16. and the central one, which is affected by 8 piles, therefore efficiency is 8 by 16. So 4 into 13 by 16 plus 4 into 11 by 16 plus 8 by 16 into 1 divided by 9 will give you 72% efficiency. So you can find the efficiency based on this, but the spacing, the diameter of the pile, all these are not being considered seriously. Let us go to a numerical problem which was asked in the last gate. A group of 16 piles are arranged in square grid format. That means 4 piles in a row and 4 rows. Center to center spacing between the adjacent piles is 3 meters. The diameter and length of the embedment of each of the pile is 1 meter and 20 meter respectively. The design capacity of each pile is 1000 kilonewton in vertically downward direction. Pile group efficiency is given by the Converse Lebarre formula. According to it, eta g is equal to 1 minus theta by 90 into n minus 1 into m plus m minus 1 into n divided by mn. Here m and n are the number of rows and columns in the plan grid of the pile arrangement. Theta equals tan inverse d by s. The design value of the pile group capacity in kilonewtons in vertically downward direction is what, which has to be computed. It can be rounded off to the nearest integer. So you know this Converse Lebarre formula. That's what is given in the problem also. And the piles in plan are arranged like this: 4 in a row and 4 rows. D happens to be the diameter of the pile, equal to 1 meter. S happens to be the spacing, which is equal to 3 meters. Substitute the values of D and S to obtain theta. You get theta equal to 18.435 degrees. Substitute the value of theta and m and n as well, which is equal to 4. And hence, you get the pile group efficiency as 69.3%. Therefore, group capacity is equal to eta g 69.3% multiplied by 16 piles, each with a capacity of 1000, amounting to 11,084 kilonewtons. So this is how the solution is. The formula is also given in the problem. It only requires you to apply the data properly and arrive at the solution. Let us move forward. Just wanted to tell you a little about negative skin friction. Please note, this is going to reduce the capacity of the pile. Majority of these times, whenever there is a possibility of the downward drag of the neighboring soil relative to the pile, the capacity is going to be subtracted. You have to be very careful. Sometimes people have made mistake. They assume that it will increase the capacity. No, it's going to be minus. And there have been many failures reported because of that. So one has to be very careful. Negative skin friction will definitely induce negative capacity. Why will this happen? It happens whenever the neighboring soil moves much more downwards compared to the pile itself. Whenever its settlement, the neighboring soil settlement is considerable compared to that of pile, you have the problem of negative friction, skin friction. So it can happen due to filled up soil which is not properly filled. Therefore, it's going to settle down. You have organic soil or peat, which again is very vulnerable to settlement. Or let us say the groundwater table is likely to experience sudden drawdown. Or in general, the capacity itself is not so good. Highly compressible soft clay. Or sometimes, if there is a surcharge on top, which is pretty heavy, which soil cannot take easily, that also may cause the downward movement of the soil much more than that of pile. So whenever the relative movement of the soil is much more compared to that of pile, you say that there is negative skin friction. And whatever I mentioned now are the conditions under which negative skin friction is a possibility, and we have to be extremely careful. So let us move forward. I would like to talk about subsoil exploration and the problems associated with that. Let me take the problem directly. The problem says that the inside diameter of the sampler tube is 50 millimeter. The inside diameter is 50 millimeter. And inside diameter of the cutting edge at the base is kept such that ICR, inside clearance ratio, is 1% only. It doesn't exceed 1%. Basically, the objective is to keep it low such that you minimize the friction on the sample whenever the sampling tube enters into the soil. The inside diameter of the cutting edge is going to be what we have to mention, express in within the two decimal places after the decimal point. So, well, friends, we all know what is a soil sampler. The objective is that soil sampler should cause as minimum disturbance as possible. Whenever there is disturbance, the values found may be very erroneous. So keep the tolerance limit, as high as possible. I mean, as low as possible, so that the efficiency is enhanced. There are a number of factors which talk about the efficiency of the sampler, like area ratio, inside clearance ratio, and outside clearance ratio. And you can see typically a sampler would look like this with different diameters. So D3 happens to be the inside diameter of the sampling tube. But sampling tube will have some thickness of the wall. If you consider the thickness of the wall in both the directions, D4 will be D3 plus 2 times thickness of wall. At the base, there will be cutting edge, which has the inside diameter lower than D3 and outside diameter higher than D4. So D1 and D2 are the inside and outside diameters at the cutting edge. So the formula for inside clearance ratio is given here. Inside clearance ratio is equal to D3 minus D1. D1 is always smaller than D3 divided by D1 multiplied by 100. So please do consider that. And now, okay, a sampler is said to be good if it satisfies the following condition. Basically, the disturbance should be minimum as possible. So in order to achieve good sampling extraction, in order to achieve improved results, the area ratio should be as low as possible, 25% or lower for soft sensitive soils. It should be, for general soils, and in soft sensitive soils, it should be much lower than 10%. Inside clearance ratio should be between 1 to 3%. Outside clearance ratio should always be less than inside clearance ratio. Wall of the sampler should be smooth and it should be oiled before utilization. And you have to also consider keeping the friction as minimum as possible. The non-return valve will permit the easy and quick escape of water as well as air when driving the sampler. So D1, D2, D3, D4 are already known. D1 is the inside diameter of the cutting edge. D3 is the inside diameter of the sampling tube. D2 is the outside diameter of the cutting edge, and D4 is the outside diameter of the sampling tube. And we know all these area ratio, inside clearance ratio and outside clearance ratio. And in the given problem, inside clearance ratio is given by D3 minus D1 by D1 into 100. So, keeping that in mind, you know that D3, the diameter of the sampling tube is 50 millimeters. Inside clearance ratio is 1%. Therefore, 1% is equal to d3 minus d1 into d by d1 into 100. d3 minus d1 is 0.01 millimeter, and hence d1 is 49.99 millimeters. So it's a simple solution, but you should know the formula to be used. So inside clearance ratio is d3 minus d1 divided by d1. Let us move forward. I'm going to talk about the stress distribution in soil and solve problems related to that. And in the previous question paper, the emphasis was only on Bosnick's theory, and that too for a soil medium subjected to point load. So stress distribution in soil, all of you should note that whenever the soil is loaded, it is subjected to stress. There are two types of stresses. One is geostatic stress, stress developed due to the overburden of the soil, and the other one is the stress developed due to the addition of the structure. There are two important theories for stress developed due to the addition of structure. One is Bosnick's theory and another is Westergaard theory. Majority of the times we are made to use the Bosnick's theory. Accordingly, we should be familiar with the equation for Bosnick's theory. And all of you should remember geostatic stress is the stress due to the weight of the soil on top of the point under consideration. So it is the overburdened soil which exerts stress quite naturally. The deeper you go, the depth of overburden increases. Therefore, overburden pressure or overburden stress is going to increase. So geostatic stress always increases with increase in the overburden pressure or with increase in the distance from the ground surface. And the other one is the stress developed due to the external load. So external load can be anything. It could be a vehicle, it could be the self weight of anybody, anything, human weight also, or it could be weight of the structure. And in this case, the stresses will be maximum near the surface at the point of contact. The deeper you go, laterally, radially you go, the stresses are going to reduce. So the major difference between geostatic stress and stress due to external loads are geostatic stress is the stress due to overburden pressure. Stress due to external load is due to the stress exerted by some weight kept on the soil. And geostatic stress increases with increase in the depth of foundation, and stress due to external load decreases with increase in the depth of foundation. So Bosnick's equation is the most popular equation for determination of the stress in soil at some depth due to the external load. The simplest one is the point load. Idealization's point load is always questionable, but it has a simple formula and easy to remember. So assume that you have a point load acting at the surface and you want to know the stresses induced at the point radially at a distance r and vertically at a depth z below the ground level. And according to this, del sigma z is given by q by z squared into 3 by 2 pi into 1 over 1 plus r by z whole squared raised to the power 5 by 2. Here q is equal to the point load applied, r is the radial distance, z is the depth, and all other things are known. Therefore, sigma z is the stress induced at any depth and at any radial distance. So that's what is said here. Q is the point load. You are considering a radial distance r at a depth z. So the point here will have the stress due to external load by this formula. The deeper you go, the radially forward you go, the value of the stress intensity is going to reduce or decrease. Well, Bosnick made his developed his equation based on several assumptions that soil is linear, elastic, homogeneous, isotropic, continuous, and semi-infinite. Soil medium obeys Hooke's law. Self-weight is ignored. Soil is initially unstressed. So you don't consider the stress already soil is subjected to. No change in volume of the soil upon loading. Top surface is level and free from shear stresses. So these are all some of the assumptions on which the Bosnick's theory is developed. And according to this theory, the stress is going to be maximum just below the point load. The farther you go from that point, the value of the stress is going to decrease further and further. So you can draw pressure bulb. Each of the contours suggests the contour of equal intensity. So the intensity of pressure is going to decrease the farther you go. And the other two graphs are for the distribution of the stress in vertical direction and horizontal direction. In vertical direction, interestingly, at an angle beta equal to 39.15, you're going to see that the normal stress is maximum. On the horizontal stress distribution, the stress is going to be maximum at a point close to the load, and farther away radially you go, the stress is going to reduce. So let us try to take a problem and solve. Problem of last GATE 2022 question paper. A concentrically loaded isolated square footing of size 2 meter by 2 meter carries a concentrated vertical load of 1000 kilonewtons. From Bosnick's theory of stress distribution, find the maximum depth of pressure bulb corresponding to 10% of the vertical load intensity. And here also, the answer should not exceed 2 decimal places. So you have the equation sigma z or del sigma z equals q by z squared 3 by 2 pi into 1 over 1 plus r by z whole square to the power 5 by 2. Vertical load intensity at the surface is 1000 kilonewtons spread over 2 meter by 2 meter. So that's equal to 250 kilonewton per meter squared. 10% of the above load intensity is 25 kilonewton per meter squared. When r is equal to 0, Bosnick's equation takes the form del sigma z equals 3 by 2 pi into q by z squared. And the stress is 10% of 250, therefore 25, equal to 3 by 2 pi into 1000 by s square. Please note that r by z whole square to the power 5 by 2 is cancelled because we are considering along the line of the load, not in the radial direction. Therefore, only unknown z is calculated as equal to 19.1 meters. Z is equal to 19.1 meters. That means at a depth of 19.1 meters, the intensity of pressure, whatever was here, it becomes 10% of what was there. So earlier it was maybe 250 kilonewton per meter squared pressure here. So stress here is 25 kilonewton per meter squared. So Z is 19.1 meter. That was the answer expected. Let me take you on to another problem here. A concentrated vertical load of 3000 kilonewtons is applied on a horizontal ground surface. A load of 3000 kilonewtons, concentrated force, point load is applied. 2 points, P and Q, are at depth 1 meter and 2 meter exactly below the load at the ground level or below the ground level, along the line of application of the load. Considering the ground to be a linearly elastic isotropic semi-infinite medium, ratio of increase in vertical stress at P to increase in vertical stress at Q is what? So, friends, you have the level ground surface, a point load of 3000 kilonewton acts at the surface. Point P is 1 meter from the surface below it, and point Q is 2 meters from the surface. Now, if you consider sigma z at P, that's equal to 3 by 2 pi into 3000 by 1 squared. Sigma z at Q will be 3 by 2 pi into 3000 by 2 square now. Therefore, sigma z at P by sigma z at Q will be equal to 4. Sigma z, that sigma z is there is equal to Q by Z squared into 3 by 2 pi into 1 over 1 plus R by Z whole square to the power 5 by 2. In this problem, R is equal to 0, therefore the problem reduces to the form Q by Z squared into 3 by 2 pi. So the required answer is 4. So here it is 4, which is an integer. So friends, let us move further. Maybe the last topic which I'll be discussing, that is earth pressure theory. All of you know the importance of it. And whenever we talk about retaining wall design, this knowledge of earth pressure theory is extremely important. Well, we have many people who have worked on it, but the most popular ones are, we do follow Coulomb's theory. We also follow Rankine's theory, which is even more popular. Coulomb's theory is more used for graphical representation. There is some difference in the assumption between the two, and Rankine theory is more convenient, more popular, and easy to adopt. So the objective here is to compute the lateral earth pressure under different situations. There are many others who worked on it, but at this point of time, focus is on lateral earth pressure by Rankine and Coulomb's theory. So Coulomb produced his theory much before in 1776. Rankine adopted much recently, and Rankine's theory was developed sometime in 1857. Well, these are all the assumptions Rankine made. I don't have to explain. Soil is considered to be isotropic and homogeneous. It's considered cohesionless. Backfill is planar, but it may be either horizontal or inclined. Rupture surface is always a plane surface. The failure wedge is a rigid body undergoing translation. Back of the wall is smooth, and hence the lateral earth pressure acts parallel to the ground. Failure is a plane strain problem. Unit interior slice. Okay, it's a plane strain problem. Well, friends, you should always know that a soil which is confined inside will be subjected to vertical pressure mainly due to the overburden and the horizontal pressure laterally under normal circumstance. When the vertical stress is much higher due to gravity, the normal stress, horizontal stress, will be reduced. So it will be sigma 3. And whenever the surface of the ground is horizontal, there is no shear stress acting unless there is a shear force which is produced. Therefore, both vertical and horizontal stresses are normal stresses. All of us are familiar with Mohr Coulomb's criteria. This is the failure envelope, failure criteria. And when a soil touches the failure envelope, it is said to be under failure equilibrium. So Mohr's Coulomb's equation is given by tau is equal to C plus sigma tan phi. All parameters explained inside. Explained. Well, at the instance of failure, that is when the stresses reach the failure envelope. We can very easily show that sigma 1 and sigma 3 are related by the expression sigma 1 is equal to sigma 3 trans squared alpha plus 2c tan alpha. Here alpha is equal to 45 plus 5 by 2. C is cohesion. Phi is angle of internal friction. Well, whenever we talk about the earth pressure theory, we need to consider two extreme cases at failure. One is active state, when the failure is due to the stress developed because of the gravitational force. A passive state is one in which the failure happens due to the horizontal push. Also, all other lateral earth pressures are in between these two extreme cases. And when the system is at rest, you have the lateral earth pressure, the condition for which is at rest condition. So in total, at rest condition, when this wall is not moved, and two extreme cases when the wall is moved away from the fill or when the wall is moved towards the fill. Away from the fill is active case and towards the fill is passive case. The three conditions are explained here. So this is a condition of at rest. The wall has not moved at all. There is no strain at all in the ground. Wall remains intact in its position. Still, the material is subjected to, you can see the soil which is subjected to some vertical stress and some horizontal stress. So that's what you have to understand. The two extreme cases are mentioned here. One case is the active case when the wall moves away from the backfill. And when the wall moves away from the backfill, you can see that the soil also, the backfill soil also is likely to move along with the wall. And all that movement is possible due to the gravitational force, the vertical force. Therefore, the normal stress sigma 1 is major principal stress, and the other normal stress in the horizontal direction will be the minor principal stress. Wall moves away from the fill. Then you have the other situation when wall moves towards the fill. That's when, wall actually pushes the fill. And in that situation, the horizontal force at the verge of failure should be large. Therefore, the major principal stress which causes failure is sigma 1, which is in the vertical, horizontal direction. Sigma 3, of course, is the overburden pressure, which can be easily computed. So whenever the wall moves towards the fill, you have a passive condition. Let h be the height of the wall. Well, we can express the three conditions, active, passive, and at rest conditions, in terms of lateral strain, and lateral pressure. Lateral or earth pressure, okay? Two extreme cases are when it is in the active situation and when it is in the passive situation. At rest condition is when there is no lateral strain. So whenever the lateral strain is 0, you have the at rest condition. And two extreme cases when the movement of the wall is towards the fill, that is the passive situation. And whenever the movement of the wall is away from the fill, that's the active situation. And this is what has to be computed. You can see that the lateral pressure will be enormous under passive situation and reduced in the active situation. Well, same thing is explained in different ways here. I'm just considering a wall here, and in active situation, this is the failure line, failure envelope. And very easily we can compute that the failure line is at 45 plus 5 by 2. The other extreme situation is passive pressure. The failure line is at 45 minus 5 by 2, where phi is equal to angle of internal friction. So you can consider a situation when you have the vertical stress sigma v, the horizontal stress kept on, decreasing and decreasing. And you reach a stage where the horizontal stress is much lower in magnitude, but opposite in direction. And that gives you the verge of failure. Exactly same thing happens on the passive situation. When you show that the maximum force which is to be applied, lateral pressure which is applied, will be enormous. So, friends, in case of passive situation, the failure line is at 45 minus 5 by 2. On the other hand, in active situation, failure line is at 45 plus 5 by 2. With respect to what? With respect to horizontal. And always remember, in active case, the vertical stress is more compared to horizontal stress. So you take a soil mass situated in active case, vertical stress is equal to major principal stress sigma 1. Horizontal stress sigma 3 is equal to horizontal stress is equal to minor principal stress sigma 3. On the other hand, under passive situation, the vertical stress is minor and horizontal stress is major. So this is the failure line for active situation. So let us take two simple problems and solve and close today's lecture. This is the problem which was asked in the previous gate. Let sigma v prime and sigma h prime denote the effective vertical stress and effective horizontal stress respectively. Sigma v prime is vertical stress, sigma h prime is horizontal stress, both effective. Which one of the following conditions must be satisfied for a soil element to reach failure state under passive earth pressure condition of Rankine? So, whenever you are considering the passive situation, you should know that sigma v is much smaller than sigma h. Or in other words, sigma v is less than sigma h. Or more precisely, sigma v prime is less than sigma h prime. So the solution is directly obtained, and answer to this question is A. Why sigma v is much less than sigma h? Because this is the passive situation, this is sigma v, and sigma h is the force which is to be applied to make the wall move towards the backfill and fade. So sigma h is much more enormous than sigma v. Therefore, major principal stress is sigma 1 and minor principal stress is sigma v. So the answer is sigma v should be less than sigma h, or sigma v prime should be less than sigma h prime. So answer to this question is A. Let me go to the last problem. As per Rankine's theory of earth pressure, the inclination of failure plane is 45 plus 5 by 2. with respect to the direction of the minor principal stress. The above statement is correct for which one of the following options? I go back to the curve. Now, for 45 plus 5 by 2 failure plane with respect to horizontal, or with respect to the line or direction in which the minor principal stress acts, is this situation. So this is active situation. On the other hand, in passive situation, the major principal stress direction is at 45 minus 5 by 2, and minor principal stress will be at 45 plus 5 by 2. So in both the situations, the direction of the minor principal stress is at 45 plus 5 by 2, and hence the answer is both active as well as passive states have the same situation. So answer, I have written it wrongly here, answer should be C. Not only the active, even the passive situation will have failure plane at 45 plus 5 by 2 with respect to sigma 3, with respect to minor principal stress. So this is sigma 3. So with respect to that, it is at 45 plus 5 by 2, both for active and passive states. So friends, with this I conclude my lectures on foundation engineering, on up geotechnical applications. I did solve a number of problems which were asked in the recent GATE 2022 in the areas of bearing capacity, shallow foundations, deep foundations, soil stabilization, soil exploration, retaining wall, earth pressure theory, stress distribution in soil, and so on. I wish you do very well in your exams. I wish you come out with flying colors. I'm going to close my lecture at this point of time, wishing every one of you all the best. Good luck to you all. Thank you very much.